Part of the problem. Somebody knew.
We're coming. So our speaker today is Julian Muñoz. He is currently an assistant professor at the UT Austin Astronomy Department. He did his PhD at Johns Hopkins, and then he was a Clay Fellow at the Harvard Smithsonian Center for Astrophysics and a postdoctoral fellow at the Harvard Physics Department. And today he'll be telling us about cosmological puzzles from JWST.
Thank you, Cynthia. Thank you all for inviting me and for coming to see my talk. So I'm going to tell you about some crazy, interesting things coming out for the first year or so of JWST. These are all very recent work, and I'm a theorist, not an observer. Some of you do observe. So I've tried to make this sort of like, my perspective on what we're learning in the areas I'm interested in, which is high redshift ionization, cosmic dawn. But I want to keep this very informal. I want you all to stop, ask me questions, like really don't be shy. I don't care if I don't make it to the end of my slides, or rather, just ask me questions and interact, okay? So let's begin. So I'm a cosmologist. I'm from the cosmology side. And when you ask how do we measure things in cosmology, typically it's through maps of the sky. The most famous one, obviously, the CMB, beautiful hot and cold spots that tell us a lot about the universe. And many of you here know this way better than me. This is what it looks like. But this is not the only map of the sky, right? As the universe expands, cools down, the CMB is emitted about 400,000 years of the Big Bang. So redshift 1,000, more or less. But the same gravitational fluctuations that give rise to the hot and cold spot that we see will grow due to gravity. And at some point, they will be big enough that they'll be able to host luminous objects, galaxies. This will happen at about redshift 30 or 100 million years after the Big Bang. That's when the first galaxies will form, and they will excite hydrogen. They will allow us to see it in maps like 21 centimeter intensity mapping and CO, C2. And over time, they will start to ionize the hydrogen around them very slowly at the beginning. But by the end of about redshift 5 or a billion years of the Big Bang, there'll be so many galaxies, they'll be so bright that ionization will be over. Now, this redshift 5 here is sort of like a benchmark, but we actually, over the last decade or two, have been nailing down when reionization ended. That's because of the CMB and also because Lyman-alpha forest, and I'll talk more about this in detail. But, this story began with ionized hydrogen becoming neutral, then it becomes ionized again. And of course, galaxies keep growing, doing their thing. You get to the local universe where you have a redshift 0, you have 14 billion years of cosmic history behind you, and you have these cosmic web of structures. You have galaxies, supernovae, you have filaments, clusters, all sorts of like cool astrophysical phenomena. But from this picture that I'm drawing here, we only understand well the beginning and the end. And these are like the pillars of cosmology. Everything we know about the universe pretty much has been built on one of these two sides. And we learn a lot. We learn there's dark matter, there's dark energy, but we don't know what these things are. And the angle that I come at this is, well, I would like to know what dark matter, dark energy are. I would like to know what the universe is made of. And it is not guaranteed that we're going to have enough information in both. There's more information in between. In particular, we don't know what dark matter is, but we know that over time, structures grow. Like you have big galaxies forming from smaller galaxies. And when you back this up all the way, we don't know how the first galaxies form. And they form in much smaller scales than the galaxies we see today. So there's sort of like a question of how the galaxies grow to be this way depends on what dark matter is made of. Like we've tested dark matter is cold, and this is what we say. Cold meaning clustering at all scales, doesn't interact with itself, it's just boring gravitationally interacting. But we've only tested some range of scales. So here, if you're a cosmologist, you can look at the top axis and the X, a halo mass of redshift. If you're coming at this, you can think of what the scale of fluctuations is in megaparsec and cosmic H. And these are the scales we've tested. The CMB lives up here, early times, large scales, very precise, pristine measurements. New measurements of celestial structure, which includes CMB lensing, Lyman-alpha forest, galaxy surveys, strong lensing. And you get near field cosmology, which I would say things around the Milky Way, stellar streams, Milky Way satellites. These are very late times and very small scales. Of course, if you look at this, you see there's a gap in our knowledge. We don't know what's happening here. We don't know what's happening at small scales in early times. So if you say about 100 million to 1 billion years of the Big Bang, this is when the first galaxies formed. This is cosmic dawn epoch. And as I said, it's a question about galaxy formation, but also a question about dark matter. If you expect the dark matter to do something weird, say to be warm, so interacting, fuzzy, all these changes would happen from small scales up. So if you're able to test what dark matter is doing at small scales, preferably at different cosmic ages to cross-check with each other, there's a powerful test of what dark matter is making. So that's one of the main motivations in this.
Okay.
Yes.
But in your previous slide, there's clearly there's a line of things that are certainly not allowed in lambda CDM, right? So you're not gonna have 10 to the 15 halo at redshift of 30.
Correct.
You have the precursor of things that are gonna come down, but that actually said, no, it's at the forbidden zone.
Correct.
Yeah.
If you were, and actually, you could plot here what is the typical halo mass forming, and it would be indeed, it would grow something like exponentially fast. So say it's like 10 to the 12 is the typical one today, maybe a little higher. So then it would just exponentially go down. These halos here would be sort of like the equivalent of galaxies or clusters. They're rare, but then eventually some of them will fall into potentials of bigger things and become satellites. Some of them will grow to be the Milky Way. So when you study things like Milky Way satellites, and you study say individual galaxies, James Webb or 21 centimeter, you're probing the same modes, just cosmological modes. I mean,
Yeah, I agree, but in terms of you're plotting what we know about the universe, and at redshift 1 or redshift 5, halos of 10 to the 15, 19, they simply don't exist.
that's correct. So these are fluctuations of the scales, right? So these are fluctuations.
It will be too big too soon.
These are linear. That's right.
Yes.
Yeah. These fluctuations here these are incredibly linear, which is the beauty in a way of the CMB. In fact, you could probe what is the nonlinear scale. That everything below it will be harder to interpret, but rich. Yeah, great question. So the other question that I'm excited about is how did reionization happen? And you'll hear more about this, but there's this phase transition in our universe. Topologically, it's super interesting. How did this actually go from, again, ionized before the CMB to neutral to ionized again and hot? How did it happen? Who did it? And finally, if you come this from the modern 21st century side, there's tensions in our lambda CDM model of cosmology. You've probably heard of the H0 tension, the expansion rate, but there's also tensions in the clustering, the abundance of clustering of matter between things in the local universe, like galaxy surveys, and things at the CMB. So ideally, what I would like to sell to you is that in the next maybe 10, 20 years, we hope to be able to put cosmic dawn organization, these epochs in between, in a similar standing to what the local universe or the CMB are. This is a long-term vision. We're nowhere near there yet, but that's the goal, is how do you get these intermediate eras to actually tell us information about what the universe is made of? And today specifically, I want to tell you about sort of the last year or two, which has been dominated by James Webb and to some extent Hubble, and what it's telling us about cosmology and astrophysics. So you'll see these two things are related, and you'll see how you need to understand both to make progress. But I want you to keep in the back of your head that the goal is not just to break things, because things might be broken, but we need to understand them to get to this complete picture of the universe, where this gap in the middle, we understand at least a little bit. So, if you work with JWST, you can ignore this slide, but if you don't, this is going to tell you the perspective of a theorist that suddenly has been thrown into what this thing can do. So if you follow the news, you've seen pictures like this, where with HST, you could take a map of a galaxy. It's a little blurry. It's a low redshift galaxy. With JWST, you have amazing resolution. You can see the little clumps and stuff. And that's all very cool. But what I'm excited about is the wavelength coverage. Is that with Hubble, you got to about 1.7, 1.8 microns with the filters that they had. With JWST, you have incredible redder coverage, the longer wavelengths. And this is not even the whole one set of filters. With MIRI, you go up to like 20 microns. So this is exciting for different reasons. But again, as a theorist, what this gets me is that I can measure things that I couldn't before. Like I can reach higher redshift, galaxies that would be invisible in Hubble. You can now see in JWST because they have redshifted here. You can measure galaxy properties you couldn't before. You're seeing the redder light of the same galaxies. Galaxies, say, at redshift 6, 7, 8, you could see in Hubble, but now you can see properties like ionizing efficiency, stellar masses, black holes, things that you wouldn't otherwise be able to see. So the whole talk is going to tell you how, when you measure these three things, you're finding weird things. The three things that we currently have access to in galaxies that we didn't before look weird. So So this is the plan. I'm gonna tell you about how, when you go to high Z, there seem to be too many early galaxies. I'll tell you what that means. When you look at ionization efficiency, reionization may end too fast, given what we know from the CMB. And finally, when you look at stellar masses, they seem to be too high. And this is where some, including my colleagues, some scientists have said that it may break lambda CDM. It doesn't, but I'll tell you why. So this is the plan. And again, I don't need to make it to the end. I'm happy to skip things. So please do ask me questions. Any questions so far? Yes.
How are you using James Webb specifically to measure its ionization efficiency?
Great. You'll see that I'm not actually using it, but specifically to give you the short answer is you measure things like H alpha, where say you look at a redshift 6 galaxy, it has a Balmer break, so it has a Lyman break somewhere here. So before with HST, you could only see like a little bit of UV light, but now you can actually see H alpha, which lives somewhere here. And H alpha comes from recombinations inside the galaxy. So you can see how many ionizing photons are being produced inside the galaxy. And then some of them will escape. So that would be the big question. But it's the red light that is giving you the ionization, even though ionization lives all the way here. Great. More questions? Okay, so let's begin. So to put you in context, what was the situation before JWST? We had the HST ultra deep fields, these beautiful images taken, an interesting story of how they actually came to be, and I'm not going to go into it. But these are beautiful images of galaxies, some stars, some nearby, some very, very far, very red. You probably have seen this when I used to have a poster of this in my room, but this actually data turns out, it's actually, you can count how many galaxies there are at different luminosities. This is what we call a luminosity function, or because it's in the UV luminosity function. This is to orient the eye, right? These are different redshifts from 4 to 8. And you can see that there's like magnitudes, abundance. Now, if you're not an astronomer, you know what this is. If you're not, let me guide you. These are magnitudes, which work the other way because we decided that, I guess. So to the left is bigger galaxies, brighter galaxies, really, with another side, there's brighter galaxies. And the y-axis is their abundance, so they're less abundant. As galaxies get brighter, there's fewer of them. And you can see also going from redshift 4 in the top to redshift 8, there's fewer and fewer galaxies as you can high redshift. Just telling you a story of how galaxies form. There's fewer of them, and over time, there's more and more and more. And again, to guide the intuition towards here to minus 17 magnitude, these are hosted typically in 10 to the 10 solar mass halos, more or less. At the left end, 10 to the 12. So these are halos that are not crazy high, right? Like our Milky Way would be here. Our Milky Way lives at redshift 0. It's a pretty common galaxy today. At redshift, say 8, it's extremely rare. In fact, we haven't even seen any. At redshift 7 or 6, there's a few of them. So something like the Milky Way at redshift, the reionization, is a pretty rare object. So this is the abundance of galaxy, and you saw put some theory lines in them. So how do you actually go and model this? You need to do something when you connect cosmology, halo masses, this is something we understand, halo mass function, to something like UV magnitude, how many photons are being emitted. So in all of this, there's going to be some amount of assumptions. I'm just going to tell you what they are, and then we can fight about how good they are. So the first one is that the UV lights come from young stars. And this is, I would say, fairly uncontroversial, but again, happy to fight about it. You need like stars that live for 100 million years or less. So you need bright stars to produce the UV light. So UV luminosity is given by star formation. So recent star formation rate. This still hasn't solved my problem. How do I connect halo masses to star formation rate? Well, so that's when you get into the second assumption, which it seems to work, and this actually could break, is that star formation rate is given by accretion rate at high redshift. So you accrete gas, something's processed, and how processed is given by some star formation efficiency, S star. This still hasn't solved my problem, but at least I've been able to encapsulate it into some F star, which is going to be some function, some complicated function of time, halo mass, whatever you want it to be, environment. But at least I can parameterize this and I can try to measure it. I know halo masses, I know gas accretion rates, and then I go and observe this. So let me tell you how I can actually go and do this. You can say, fit the data with something like abundance matching or a parametric model. But when we do all this, what we end up finding is this star formation efficiency, which these authors call epsilon, it's the same thing, star formation rate per gas accretion rate. looks like a double power law as a function of halo mass. So bigger galaxies are more efficient up to a point, and then it seems to kind of turn around. This is because of feedback, right? If halo mass was irrelevant to the question, this would be a flat line. This is not a flat line because at low masses, you get stellar feedback, winds, supernovae, things that eject gas. So then as the mass gets lower, it's easier to disrupt. So it's less efficient in forming stars. When you go to high masses, we're not sure, but it's likely AGN. Big mass halos will likely host black holes that they quench galaxies, don't allow them to form stars. So rather than take any one of these possible options, what you can say is come at this very agnostically and say, hey, I'm just going to parameterize this. This looks like a double power law. So I'm going to give you some amplitude, some location for the knee, and then two indices, alpha and beta, for the faint and the bright end. These are going to be free parameters. You can make them vary with redshift. And you fit the data with this. It's a very, very simple model. There's no hydrodynamics here. I haven't really invoked any like specific connection star formation rate. This is just very empirical model. And when you do this, yes.
Could you explain why you know that is inverse power law? I don't remember.
I don't know.
Okay.
But if you look at it, kind of looks like it.
Okay.
So it's a model comparison question at the end of the day. Is, I haven't measured this quantity, but these quantities, star formation efficiency, this is the free parameter of my model, right? This is like what's connecting the part that I know to my observable over here. So then I could parameterize this in any way I want. And what I want to show you is that this double power law works for the quality of the data that we currently have. And I'll tell you actually how a high redshift, it might not work. I'll tell you exactly in which way it'll break. More questions? Okay, so I want to highlight work done by Nash Shakti, who wrote this called Galumi. If you are into the Monty Python CMB likelihood world, this actually Nash was a postdoc at Hopkins. Wrote this code. It talks to Monty Python, so you can do MCMCs like you could for any CMB data. At different dust, as different halo galaxy connections, all this idea of star formation efficiencies. And the main highlight of the point is that it's very fast. You don't need to run a simulation. This is all analytic, takes about milliseconds to run. So you can actually MCMC over astrophysics, over cosmology, whatever you want. And he had stochasticity, which we'll get back to in a second. But when you do this, you can fit all the luminosity function data that I showed you. So that's the lines I showed you at the beginning. And that was all Hubble. Remember, now we're going to talk about James Webb. What did we predict for James Webb? So this is one of the predictions from 10 years ago for Charlotte Mason. These are all the luminosity functions. Again, you can fit them with these type of models very well. But when you get to redshift 10, which is the green line, as you can see, for the typical volume we observe and the typical magnitude cut that we expected, we typically expected over one few galaxies at redshift 10. When we turn James Webb, this data from Sears, at redshift 10, 11, 12, we see dozens of galaxies. There's an order of magnitude more galaxies than we expected. Some of these are squares. Squares are spectroscopically confirmed. There are circles, have not been followed up. But you see, even at redshift 14, 15, there's candidates. I would warn about the quality of these. These are very sketchy. But at redshift 10, 11, 12, there's a lot of galaxies. Again, an order of magnitude more than we expected. As I said, some of them have been spectroscopically confirmed. I just want to flash this plot to say, when there's follow-ups, there's like sort of like lower bounds, and they seem to also be agreeing with the photometry. But the main takeaway of this part is that when you measure luminosity function versus magnitude, same plot I showed you for Hubble early on, but now you do with James Webb at redshift, say, 11, your data is well above these models. So these black dash model is the same model that I've told you used for Hubble, works amazingly well at redshift 4 to 8. It breaks at redshift 11. Yes.
Is it fair to say that some of this tension, someone who's kind of on the outside of the JWST, too many early galaxies side of things, that it's not just there's too many halos, but there's too many bright objects?
Yes.
So it's not just about number density, it's also about that connection.
That's right.
Okay.
And that's going to be the solution.
Okay.
Yeah, good student, jumping ahead. Okay. I love it when I'm teaching a class and like a student actually says exactly what I'm going to teach. It's great. Yeah, so indeed, you need to mess up with the number of halos. You need to mess up the number of galaxies. But in fact, galaxies above some magnitude cutoff, -17, these are pretty bright, actually. So someone gives you this, and of course, you could say, well, I'm just gonna increase the number of halos, I'm gonna move this curve up. But you don't have to. In fact, one of the things that we expect is the high redshift, the connection between halos and galaxies is gonna become less stringent. So let me tell you actually what this means through a cartoon. If I had no stochasticity, I can populate galaxies onto halos 1 to 1. So say, I tell you, the size of the circle is how big the dark matter halo is, and the color bar is how bright the galaxy is. If there's no stochasticity, big halos host bright galaxies, small halos hold faint galaxies, situation is solved. A high redshift, I know that I have dust that may become less or more important. I know metallicity will vary. I know star formation rates themselves, star formation histories are going to be very bursty. All these things contribute to changing the halo-galaxy connection, where I can have small halos that are bright and big halos that host dim galaxies. Yes, sir.
Ignoring, just ignoring modeling. Does HST and JWST, do they do the observations here on agree? Is there a lower limit to JWST that we cannot go below it? Okay.
You can, but so typically there's been all the programs that were, I don't want to talk too much about, I don't want to say too confident of a statement of observation, because I'm a theorist, but my understanding is there's not been a big push to redo Redshift 6 observations with JWST necessarily, because HST can do it. So a lot of the programs, the filters they selected in the very beginning, the filters were redder, so you can go towards higher redshift objects. But my understanding is when you combine the data, a redshift 8, for example, they agree fairly well. Okay. A redshift 8, you do find agreement, and then you see sort of like a departure redshift 9, 10, 11. So it's not like JWST is poorly calibrated or anything like that. If you're thinking of a systematic, I would argue that's likely not the case. There's been a lot of fights about the photometry calibration, and my understanding is that's settled. Okay.
Can you go back to the luminosity plot?
Yes.
So, yeah, so. Yeah, you can either move it up or move it left, and can you just, how sensitive is the knob of changing the IMF, the more top heavy, get that curve?
Great, so that vary. And I will, in terms of how much brighter you need to make them, like a factor of 4.
Yeah.
So the question really shouldn't be, I mean, of course, the IMF will change, there's many reasons to expect top heavy or bottom light IMF a high redshift. However, the question is, why is this a redshift 11 and not a redshift 8? Or are we misanalyzing the redshift 8 in some way?
Yeah.
So actually, part of the point of the talk is going to be, how do you distinguish this?
Yeah.
There's going to be 2 different scenarios that can work. How do you distinguish IMF versus burstiness?
Well, and which one's easier? Which knob is easier to fix it, right?
In a way, the IMF is easy because we don't know.
Yeah.
You can do it.
Like, it seems hard to populate a bunch more halos, where it seems easy to just turn a knob on IMF.
But I would argue that part of the problems when we've done all these like models in the past, I include myself here, it's like all these idea of stochasticity, burstiness, we kind of like swept it around the rug. Like, it's fine, you know, just connect them, like abundance matching is fine. But actually, we know from hydro simulations, there should be burstiness.
Yeah.
And now we're actually getting at individual galaxies and measuring star formation histories versus time, and they vary a ton object to object.
Yeah.
So there's still like a longitudinal argument of you study the same galaxy, goes up and down. Is it the same as taking all the galaxies? But there's some ergodicity argument you can make about there should be variation, and there likely might be both.
Yeah. Yeah.
Yes.
Just to add on to that question, so the plot you're showing is about ethnicity. So if like varying the IMF, for example, doesn't affect this, or maybe you're gonna say it does, like what actually drives this like stochasticity in the galaxy?
Good. So there's different physical mechanisms that can do it. The one that is obvious is just actually star formation histories. So you have a halo, has accreted some gas. How the gas is accreted into the halo varies a lot halo to halo, and it depends on things like the environment given. So there's an idea of just the actual accretion rates will be different. Then how the gas is processed inside will also be different. They give you keep feeding gas with a particular distribution to a halo, to a galaxy. The way the feedback is ejecting the gas and the gas is recollapsing, this will give you burstiness. So it will be on-off periods. And you can think of it as a duty cycle, but you can think of it more generically. How loose is the connection between halos and galaxies? So there's physical mechanisms that should be there. And the question is how important that. And there's also line of sight, by the way. Yeah, like dust could be inhomogeneous, and then you happen to catch a very dusty sideline versus non-dusty sideline as well.
While we're stopping,
Yeah.
So there's a, the problem, you can probably like dissect it in a slightly different, so. The stochasticity, I think, people have not been paying attention, and it's actually quite relevant, particularly when you're looking at galaxies that are actually smaller.
Mhm.
Because I think that's where things get, messier.
Yeah.
But I think there are like two issues which maybe should be important to separate. One is like kind of like the details, which is the dust, the IMF, how red they are, all of the things that are missing the brightness of the gas that you're measuring.
Yeah.
Because I think it's something that it should be probably relevant to say is that you are, with JWST, you see the gas that is shining. And the only thing you know from cosmology are the halos that are the dark matter, which are kind of like truth. That's kind of like the truth.
Mhm.
And that's kind of solid. The rest is kind of like the weather,
Mhm.
right? It depends on the initial conditions and the measurement you have. It could go, it could go either way. So this is the question. So is the stochasticity that you're introducing now giving you dramatic changes into what is called the, the light to mass ratio?
Yes.
Which is like the amount of gas that you see, which is baryonic matter compared to the dark matter, which is what you trust, which is the fundamental and hopefully what you should not be breaking.
Yeah, so yes, and I just have this slide to show you
Okay.
how these two things are degenerate.
Okay.
But how you break the degeneracy between, you can think of like a specific brightness, like star formation rate divided by halo mass. Like something that is purely dark matter I understand, and something that I observe star formation rate. And that depends on, even if you want to look at UV luminosity, depends on, you said metallicity, dust, all these things. How does that change when it changes stochasticity? So indeed, and by the way, I want to say that when you look at these silly models, like the one with the double power that I was showing you, there is secretly more flexibility here than you expect. Because if your brightness, say the IMF changed with halo mass in some way, because at the end of the day, I'm just calibrating UV luminosities. They say like there's some behavior on the UV luminosity halo mass that we capture in this alpha star, for example. So this is not the true halo galaxy connection. This is the effective halo galaxy connection of what I observe, which is in this case UV luminosities. So there's a little more flexibility in these models than you expect, but of course that comes at the cost that you don't get to see the truth, the ground truth, so to speak. A lot of questions. So if you make galaxies bursty, you get something like this. Why? Is because all of these small mass halos that usually would be very, 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 very faint, now they can happen to be bursty. There's a lot of low mass dark matter halos, and they just pick up and they become bursty. You can think of it as changing the knee of the luminosity function, but then, the low mass knee is all the way there, super faint. So burstiness can explain this, but as a kid also mentioned, you can have galaxies being brighter. You can have high UV star formation efficiency, could be from pulsar stars, could be feedback-free starbursts, like Avishai Tekel was. These two models essentially could explain the data, and you can argue at length about which one, if this point prefers this or this, if this point prefers one or the other. But as you see, they both are in the right ballpark. Early galaxies are either brighter or more bursty than we expect. So which one is it? So this is a problem that existed at low redshifts. And again, we've swept totally under the rug because we could explain the data. So here's the redshift 4 luminosity function from Hubble. Much better understood, beautiful data over the last 20 years. And then you can fit the model where you can vary burstiness and star formation efficiency. So here's what I mean. Here you can think burstiness, this is how many magnitudes there's variation in a galaxy that is in the same halo. Here's star formation efficiency, which again includes some UV efficiency as well. And all these different points are within the 2 sigma contour of the data, and you see they fit the data very reasonably well. But essentially you could be very bursty but not very efficient, or less bursty but very efficient. So there's a degeneracy actually between these things. And you see this space here for a second figure, so I'm going to tell you how to break it. And the answer is by using clustering information, using the bias of these galaxies. This is something we do routinely at low redshift, right? So like redshift 0, people want to look at this and like, yeah, obviously. But high redshift has been difficult, partially because you don't have enough samples, but also partially because you have to interpret. But the bias of these galaxies changes a lot when you go from bursty to non-bursty. Bursty, like the red, is going to be dominated by small mass halos that happen to be kicked up, become bright. So the biases are low because they live in small mass halos. As you make it less bursty, you see the bias goes up and actually becomes more like steep, like it would be for halos, right? For very, very massive halos, there's a very significant bias towards the heavier. Yeah.
So it's probably a very stupid question, but to what extent are these mechanisms competing versus?
Right, there's both. So you can think of in this 2D plane that I've shown you here, which again has a lot of other parameters are marginalized over. The question is, it's not like I live here or here. I live somewhere. Where do I live? An interesting thing is preliminary data that I haven't folded in the calculation. This from Subaru Hyper Supreme Cam, redshift 4 galaxies, seems to suggest the bias is high. So you live somewhere like, this 2 point, you live somewhere like here, like low stochasticity, high star emission efficiency. Yes.
So what is the bias correspond to as an observable? Is it just like how Western
Is the-
galaxies of magnitude they are?
Is the amplitude a 2-point function? Well, the bias square is the amplitude 2-point function compared to matter. So higher bias means galaxies will live closer to each other.
Can you calculate this by Bin's magnitude?
Correct. So this is by different bin magnitude. That's right. And in principle, you can do this analysis by integrating up to a point, and I'll show a data point that does that. But ideally, you just want to bin it in magnitude, just work with each other. Great. So let's go to redshift 11, where we have this problem. You have, again, the pre-JWST model, too low, and then you have the blue, high star emission efficiency, IUV luminosity, IMF, the red is bursty. They agree where the data lives. You see here, they disagree, but here data is tricky. So I'm gonna show you two examples of data people have put here. GLZ11, which may very likely be hosting a black hole, so it's not just a galaxy that is bright. And then this other data point here actually has a secondary redshift solution of redshift 3. So it's likely an interloper, not a real redshift 11 galaxy. So here it's hard to measure things, but we'll get there. But these models that agree very well, when you look at their bias, it looks dramatically different. The bursty model, the red, is very low. The star formation efficiency model is very high. And notice these biases are all huge compared to low redshift universe, which is to be expected at high redshift galaxies are rare. This is a forecast of what you can be able to do with Cosmos Webb or with Roman highlighted survey. But there's already current data from Hubble, and this is integrated to brighter than here from Dalmaso et al. This seems to indicate a preference for the blue model, which again agrees with what Subaru says on low redshift. But I will warn about taking it too seriously because it's looking at very small scales where you don't really measure the bias. You're measuring like a one halo term, if you wish, which is you cannot just interpret as the bias that I've been talking about. So like the bottom line is, if you want to break degeneracies, 1-point functions, things like the luminosity function, are degenerate. Just counting how many objects. I don't know if they're bright because there's few of them and they're all bright, or like they're just scattering around. So you need to do things like 2-point functions to actually learn the truth. Questions before I move on from that?
So if the story that you're telling us is that as we would expect, so the blue line will be the objects that are more clusters,
Correct.
right? If they're more clustered, stuff happens faster, and then there's less, there should be lesser formation rate.
No, good. No. So
What is the,
good. So
and then one compensates over the other. What is
So
it?
in the blue, I'm making all the objects brighter. And then it kind of looks like this picture where there's no stochasticity, but all the objects are brighter. But still, because all the galaxies will live in heavy halos, the heavy halos cluster more. So it's not like the clustering produces the brightness. It's that because the galaxies will live in the heaviest halos cluster a lot. Whereas in the bursty case, you can think of it more like shot noise. Like whichever halos happen to be populated with galaxies are not going to be necessarily clustered, are going to be more homogeneously distributed. So the 2-point function, the clustering, the power spectrum, if you wish, of bursty galaxies is going to be lower. Again, not like an order of magnitude lower, but 10%, 20% lower because the halos are more homogeneously distributed. So it's all about connecting the galaxies to the halos.
Okay, but in the data you have from Subaru, from HSC,
Yes.
that was, I'm assuming that those were mostly. Do they have some clustering? So that's telling us that the galaxies that are more clustered have a higher bias? Is that
That's
right?
correct. That's correct.
Okay.
Yeah. So this is measurements of the correlation function, angular correlation function
Yeah, 2-point correlation
Yeah.
function, okay.
of galaxies of different magnitudes from Yuichi Harkana.
Okay, so when you look at the more clustered,
Mhm.
they tend to have less, less objects, they're
Yes.
less.
So
okay.
another way to
The
put it is,
the number counts will be smaller, is that what it is? Something like that?
you can think of it, yes, that is true, but I think the way that I think of it is that as the objects get brighter, they cluster more strongly, which is an indication that as the object is brighter,
Yes.
they live in heavier dark matter halos. So if MUV was uncorrelated with halo mass, this would be flat, the bias would be exactly flat. Because you would just see, that dark matter halos gives you the bias. Good, yeah. Yes,
Yeah, I wanted to ask about, so the bias is sort of measuring like the mass of that environment and also like an environmental thing. Do you worry about those, like preferentially having more gas accretion to give them these? Is that like built in, or is that like a separate effect that you try to distinguish between?
good, that would build into the bias, so in a way, that would, that's all into the measurement you do of the bias. What you're describing is what some people refer as assembly bias, is that like, rather than just like the dark matter halo itself, there's something on my halo galaxy connection that depends on density.
Yeah, like it makes it easier to make a brighter thing faster because you have more gas and because it's starting forming earlier. Like this.
So I would say this actually is something that's still not well known at high redshift. When we look at low redshift, only recently I would argue we've actually got a good handle on it. At high redshift, there's an idea that it should be smaller because redshift 4, your bias is like 2 to 4. At redshift 11 is like 8 or 10. So like if you add some environmental dependence, it's smaller than just how rare the halos are. But that is not settled. So I would argue we need to run simulation to understand this better. Yeah, in a way that is built in the observations, but not in the models. Yeah. Yes.
Let's go. Does your model or do your models have description for each move fraction, like number of galaxies or?
Good.
Like each and every-
It is to some, so my models only model galaxies so far. But the data that we get, for example, from Subaru is clean because they have spectra and they actually get the AGM fraction versus galaxy fraction of different NUVs. So then you have to be able to compare apples to apples. So when you go towards the bright end, here maybe half the object will be AGM or more, and then you actually need to be able to know which half. So here just throw it out. But you get towards the fainter and fainter objects, the fraction will be smaller, but it's still some fraction.
All the photometric observations.
Yeah. That's right. It's very hard to get a spectroscopic sample big enough to do this. Maybe photometry, yeah. Awesome, love it, okay. So, as the first question, so many early galaxies, we don't know why, we're gonna find out soon when we measure clustering. Let's talk about reionization. So let's change from galaxies to like their environment. And we said like galaxies reionize the environment they live in, they create these bubbles. It's topologically complex, right? There's all these bubbles, they're small, they merge, they become bigger. But really at a mathy level, it's very simple. Hydrogen starts neutral, and then you produce ionizing photons, they hit hydrogen, so at some point it's halfway through, and then at some point it's fully over. So when you think of it as an accounting problem, really there's like two things you need to worry about. How many photons you produce, how many photons you need. That's it. So if you were going to do the math, you can say how the ionizing fraction, so this is 0 to 1, the fraction of hydrogen that is ionized in the universe. It depends on how many sources you have. You have galaxies, black holes, things that emit ionizing photons. You can put dark matter here, if there's dark matter annihilating, for example. And you have 6. So you have some amount of hydrogen atoms plus some amount of recombinations, right? Because hydrogens will recombine every once in a while. So if you're going to split it, the thing that is fairly uncertain, or the most uncertain perhaps, is sources. So you talk about galaxies, let's talk about galaxies for now only. Then you can have how many ionizing photons are produced, depends on how many galaxies there are. So you integrate the UV luminosity function, the same one I showed you before. So how many galaxies times how many ionizing photons per galaxy is given by the psi-ion parameter. And then how many of them escape, what fraction of these photons that are produced in a galaxy actually escape into the intergalactic medium. That's because ionizing photons are very good at ionizing. So they might just ionize something in the galaxy, recombines, never leaves. So there's the math. Now let's talk about, we're taking a little historical tour of how reionization has evolved over the years, starting about 2000, where we knew pretty much nothing about reionization. I know some of you maybe like have worked on this, so like I want to hear your thoughts about this. So around 2000, we had best CMB data was boomerang. Reionization could happen anytime, basically. It wasn't until 2001 that we had the first quasars that were able to measure the Gamma-Peterson trough. That's when we know reionization was reaching 5, 6, 7, something like that. Now, very quickly, WMAP turned on. We had some quasars, but the first WMAP data suggested reionization happened at redshift 15 or 16. And that was wild. It was very hard to make reionization this early. You needed a lot of ionizing photons to make it happen this early. And people cooked up models with POP3 stars, dark matter, many different things. Over time, WMAP came down. By then, we had the first Hubble surveys with the advanced camera for surveys, like it's a good Hubble Deep Field. So we had galaxies up to redshift 6, 8, and then this number went down, but still was like redshift 10. It was a little uncomfortably high at the time of WMAP. You needed more galaxies than you have seen, or higher redshift galaxies than you have seen to give rise to reionization. But now, when Planck turned on, around 2015, also Lyman-alpha 4 data become even better. This went down. And by that time, again, we reached higher redshifts. So circa 2015, when Planck turned on, you see the optical depth settled to reionization about midpoint redshift 7 or so. And at this point, you can see how quickly the community kind of like converged on, well, we can explain reionization with galaxies. So there were different groups, in particular, Robertson and Richard Bowens. They said, given some reasonable parameters for ionization efficiency. So this is what you get from Spitzer data back in the day, modeling. F-escape about 20%, so all right. You get an ionizing, like the evolution of reionization, functional redshift, kind of fits with the data. Starts fully neutral, becomes ionized, goes through all these data points. When you look at the optical depth for the CMB, it's integrated. So you should look at the value of high redshift. Agrees with the Planck measurement. So all is good. We've explained reionization. Yes.
So those parameters you show, is that like per galaxy or is that like kind of per slice of the universe?
These two numbers?
Yeah.
Those are per galaxy, but they are taken to be constant in this. I will show you, you should make them vary with galaxy properties.
Because I was gonna say, certainly with JWST, I think you can get proxies with both of these things
Mhm.
from your spec, right?
Yes, great question. Love it when you get ahead. Yes. So how we solve reionization? I think the fact that I'm here tells you no. And the fact that still people writing proposals on reionization. So do galaxies do it all? Maybe. AGN do it. I'm not gonna even include AGN, but you'll see how that gets tricky. So this is the situation after Planck. But now we have JWST. So this is a spectrum taken by Hakim Attack of a very faint galaxy, magnitude -15. You don't need to know what all the lines are, but I just want to point you here and here. These are Balmer lines. They're incredibly bright. What that means is that there were a lot of recombinations in this galaxy. So this galaxy was emitting ionizing photons, and some of them were being absorbed. Remember, the escape fraction is not 100%, it's actually pretty small. So most ionizing photons don't escape. In fact, the ionized hydrogen recombines, goes through Balmer. So from the height of this Balmer line, you can actually find how many ionizing photons were being produced. And you can take results from this or from like these other two papers, in particular from Simmons has the larger sample. So you can take that and the new ionizing efficiency is larger. So you see something where if you plug this in the same model we had before, now ionization ends too early, redshift 80. And the CMB optical depth is huge. That's a problem. But of course, what I hadn't told you is there's a secret in all this, which is you care about the escape fraction, remember? You don't know what this is. Here I've kept it to be 20% because that's what these folks took. But now we may have better data on this. And in fact, we do. You cannot measure F-escape at high redshift because all the ionizing photons by construction ionize hydrogen. They're doing re-ionization. They don't get to you. But you can do this at redshift 0. So different folks over the last decade or so have been building this sample. This is from the LCLTS, low redshift Lyman continuous sample survey. And they measure how F-escape correlates with different quantities. And they find good correlation, though there's scattering, with the far UV slope beta. So this is the slope of the SED. To give you an idea, this is the color of the galaxy. And it's telling you that bluer galaxies have larger escape fractions. There's a lot of lines in here, but what we want to know is this line here is what you will get if you only had dust. So dust reddens galaxies, so more dust reddens, and more dust also absorbs. So that's why there's this correlation. But of course, there's more to it because there's neutral hydrogens captured here as well. This is purely empirical, right? I haven't actually modeled specifically what's happening inside the galaxy. It's just that bluer galaxies have higher escape fractions. But the interesting thing is that one of the year one results from JWST is interesting is galaxies high redshift seem very, very blue. So this is a typical median or mean slopes at redshift 7, magnitude -17, they're like -2.3 to 2.6. Early galaxies are very, very blue, which means they should have high escape fractions. So if this relation holds, it's a huge if, because the high redshift universe is very different from the low redshift universe. But if it holds, you can go to this plot And the low CF escape gives you even earlier ionization, even higher optical depth. So this is in disagreement with the CMB, also in disagreement with the Lyman-alpha forest. Because like it has to end at redshift 5.5 or so, not at redshift 8 or 9. So at face value, you take all JWST data, you take these low redshift insights, and reionization should end earlier than we expect, earlier than we know. So what's going on? So let's generalize this a bit. And I'm going to talk about, when we talk about this source term, right? There's all these terms that tell you how many galaxies there are, how many ionizing photons, what fraction escapes. The only ones you can directly measure really are how many galaxies and the ionizing efficiency, because you can get spectra of galaxies. F escape, you only measure at redshift 0, so you need to assume, you need to figure out how it's high redshift. And there's a cutoff. Like what is the faintest galaxy that contributes to reionization? This number we don't know either, but we can get some constraints. So let's put these two numbers we don't know, one on the x-axis, one on the y-axis, and let's put some lines here. Let's see, what do you need? So first, you need to produce the right reionization. So here, say in terms of the CMB, the right optical depth. So if you make the cutoff fainter, there's more photons being produced, so the F escape has to be lower, right? As there's more and more galaxies, the photons escaping from each has to be lower. And if you're above this line, there's too many photons for the CMB, so reionization is too early. If you're below the line, there's not enough, so you don't give rise to reionization at all. So this is sort of like we need for the CMB. Then you need to reproduce this low redshift F escape. As I said, there's this correlation between slope and F escape. You can put it in this plot, and it looks like fainter galaxies are bluer. So like this blue line is kind of what you need. And they intersect around here. So this is where you want to live. But now, from JWST and HST, we know there's no cutoff down to about magnitude minus 15. This is from directly looking at the luminosity function and seeing there's galaxies all the way down here to minus 15. That's the deepest we've gotten so far, high redshift. So these three regions do not overlap. Either you have a cutoff and you live here, and then that's a problem because we see galaxies all the way to minus 15, or maybe the blue is wrong and you live somewhere where the red and the green intersect, but then you break with these low redshift studies. So at face value, if you take JWST, which is, say, you can think of like the green, and you take the F escape, you need to live all the way up here, way above the CMB. And I'm not willing to give up the optical depth in the CMB. So something is wrong. So, yes.
What dominates the escape fraction? Is it dust or gas?
It's a great question. So if you look at the plot that I showed, and this again, to be clear, this is redshift 0 to 0.3, right? So this might be very different at high redshift, and there's reasons to expect it should be different, but if it was only dust, all the points would be exactly here.
Yeah.
So the scatter from this point down is because of H1. It's because of gas. Now, these points are colored. I didn't tell you what the color is. This is from like John Chisholm's paper. The color is the relative, so the relative F escape. So how much is contributed by things that are not dust. So you can actually see the bluest points here, basically just all dust. The yellowish points are H1. So you think dust gives you some correlation, some slope, and H1 gives you something, but it just what looks like a scatter up on this. Again, both contribute. I would argue maybe comparably, right? Like if you want to get an escape of 10%, you want to be somewhere here where like dust has done something, and then a lot of it is done by H1.
Yeah.
But I would argue it'd be very, very difficult to get direct access to H1 high redshift. So beta is like the one empirical thing you have access to.
But so as they get more obscured as the escape fraction.
Obscure is this way.
Oh, sorry, I was looking at I was assuming that the fraction of escape should be proportional to dust, right?
Yeah.
Always.
Yeah.
Okay.
To like dust column.
Yeah.
So the other way, 1 minus F escape. Yeah, exactly. Yeah. So how much you absorb is how red you become.
Yeah.
So there's a subtlety here, which is I don't know what the beta would be without dust. But they actually, I mean, there's something they correct for. This is, yeah. The other thing, of course, you're targeting a redshift 0 sample, and I'll say Vandals have done this at redshift 3 and find the same correlation. That doesn't mean that it works at redshift 7, right? It just means that redshift 0 to 3 seems to work out. Redshift 7 could be an entirely different beast.
Yeah.
Yeah. More questions? Okay, so we have a problem. So what are ways out of this? So one is that maybe these psi-ion measurement, these efficiencies are biased high. So here's a complicated plot, but I'm gonna walk you through. So this is UV magnitude, like always, faint is towards the left. Here's this parameter, the ionizing efficiency. Pre-JWST, we lived in this gray region. You can see all the JWST measurements are coming higher. These are different redshifts. But you can see some of them are spectroscopic. So Tony Paul and Hakeem Tech have spectroscopic measurements, and the rest are photometric. They all are higher. Some of them grow towards the faint end. So the Simmons is what I showed in the previous plot. When you do with the Ensley, for example, with the red lines, you plot a line through it, or you take it like something else, you'll see that they're all high. You can take something like 25.5. It's like Bolmar, the lowest point here in this Ensley sample. If you take 25.5, you still find a problem. You still find that reionization ends too early. So you have to be even lower, or you have to be this plus something else, this plus a cutoff, for example. So if you turn on tomorrow and you see a cutoff at -14, this could do it. But then you need a cutoff at -14. The other thing is maybe there's more recombinations. So I've told you about like hydrogen will recombine. I've taken some clumping factor, which is just basically like how often, we'll tell you how clumpy hydrogen is, how often they'll run into each other, electron protons and recombine. You can make it 20 instead of 3, so 7 times more recombinations. You're still not quite there. But it could be, in fact, Fred Davis argues that you need something like this for the Lyman-alpha forest. Maybe you need more recombinations than you expected because the mean free path is very short. But each of them on their own cannot do it. If you put them together, maybe you would push, but these don't seem like it's enough on its own. So you can just bring the big guns and say, okay, what if someone is wrong? What if, say, there's a cutoff and we just like all the lower measurements actually they're just wrong. We're just seeing some on turn of some galaxies and not the off mode. What if it's a cutoff, say -17? This, for example, Jorrit Mathie argues with like Lyman-alpha emitter driven reionization. Or what if the F escape is very low? Like a high redshift, all these scaling relations break and F escape is very low. And you can think of this as two sort of modes of reionization. Low F escape with no cutoff looks like democratic reionization. There's a ton of galaxies, each of them contributes a little. If you put a cutoff here, F escape is high, so there's very few galaxies. So there's a few galaxies driving how reionization happens. And the good news is you can actually tell. These give you slightly different reionization histories. If you put a cutoff, you get this black line. So it actually happens relatively quickly. That's the black line over here. Versus in a democratic model, like the red, you actually still make F escape, it's low, and it goes more slowly. But right now, these two models need something to break, need one of our observations to be wrong. And it could be that it is, but they need one of them. Yes.
This is a basic question. Is this cutoff? Is this an observational point or is it a physical point about like how bright a galaxy needs to be to contribute to reionization?
It's both, in the sense that there's a physical point at which galaxies will stop existing during reionization from, say, photoheating feedback. So you'll be just ionization fronts, they will blow up the gas, and there'll be galaxies that are too faint, they just don't exist.
I see.
And this is at -11, so this is where this point would be more or less. But that's ballpark, right? We don't know. Then there's an observational point. You can actually go and observe galaxies. How faint do they get? And they get to like -15, more or less. And in fact, not only they exist, but they emit photons. So you can see this here. Hakeem's sample reaches from -15 to -17. So there's galaxies at magnitude -15, more or less, that are actually emitting photons. Okay. But this sample in gray is about 6 galaxies. So it could be that we were lucky and we caught the 6 galaxies that we're on. And for every 6 galaxies on, there's 100 that are off or something. That would mess up the luminosity function, but you know what I mean.
Yeah.
Okay. Yeah. So it's both a physical reason why there will be a cutoff, but there's also an observational question. Yes.
So I see you can do like the analytic model thing, but then people work on this from the simulation side, like trying to like, I guess, how do the simulations compare to the digital?
In which axis?
I guess the plot before, the one with the tau CMB.
The one with,
You have people like try to like populate this with like simulating.
good. Yes, in fact, yeah, you can put like, for example, Thyssen or Sphinx in these plots. The warning against it is in most of these, like Thyssen, you're only above the atomic cooling threshold. And however feedback's implemented, you might not reach the faintest galaxy. And then measuring if escaping simulations is notoriously difficult. There's a lot of sub-resolution problems. So you could put lines to what like the different things do. For example, as I did by Jockey Rosdahl Sphinx that argues that F escape has some behavior with magnitude where like it goes up and then it kind of turns around. That is not what we see in observations. It seems like, again, if you look at low redshift, it doesn't seem to do that, but it could do that. So people have tried that. That would be an interesting question to see what are the different models that the hydro systems give you. Yeah. Good. So you can separate it. And the last point I want to make is that this should remind you of the luminosity function in that this is a 1-point function. This is the average reionization history. The future holds that the future is in measuring the clustering. How is ionization distributed? You can make up two models, democratic and oligarchic, that give you the same evolution of the initial fraction, an average, but very different history, different clustering. And this is something you can measure with 21 centimeter, KSZ, Lyman-alpha, things that actually measure reionization bubbles. For example, these two models, again, almost the same ionization history, but very different, say, bubble radii. Like the black model, the oligarchic model, because the galaxies driving it live in big halos, they're more rare, they're more clustered, they give you big bubbles, compared to the democratic model that gives you the small red bubbles. Yes?
I've heard of the oligarchic one, but could you just describe quickly what the democratic model?
Yeah, so democratic is instead of, if you want to think of it in like terms here, the oligarchic has a big cutoff. There's a few bright galaxies are dominating reionization. So the oligarchs are providing all the photons. The democratic is the opposite. There's a lot of faint galaxies that are providing the photons. So it's like, is reionization very diffuse or very concentrated? And that's something that you really need to measure maps to actually be able to tell. Like the average history will always be questionable because you're measuring the 1-point function. You need higher point functions, 2-point functions, et cetera.
So another like dumb question I have, if you just look at like cosmic new and see like the outcome, so.
Well, but then the question is does this work if you stand to redshift 2, right? Like, it's the same question for the F escape. Like the gas content of the galaxy may be different. Like, it's not enough to look, and people argue for oligarchic models, look at redshift 2. They say, if I take the redshift 2 Lyman-alpha emitters, at redshift 6, they should dominate. But of course, then there's an extrapolation there. Yeah. So I'm gonna end here. I had another whole point about breaking down CDM. I'm happy to talk about this offline, but I'd rather just stop here and take any questions. Thank you.
Thank you for the top on the question, but for the ionizing bubble, do we still assume that they are like isotropic? Like
No. They don't have to be. They can be like, you can see they have all sorts of weird shapes. But the important thing is, are they bigger or are they smaller? So when we talk about bubble radius, really we should talk about volume to the 1/3. That's the relevant, like, it's not a real radius in the spherical sense. You have an ionized region, what is the volume to the 1/3? Yeah. That's important because they're not spherical. They're only spherical on average. If you stack 1 million of them, you stack 1 million of anything, the universe is isotropic, it would be spherical. Yes.
So what amount of data are we going to need, or how long is it going to take for us to get this type of clustering information for both of these?
That's a great question. For the first point, for the galaxies, that is, could be today. Because Cosmos Webb is already observed, just like they haven't done the 2-point function, partially for human power reasons. So if someone did it, it could be today. For this, it's a little longer. So I would say out of all these, Lyman-alpha is like, you can do with JWST, but it's very hard, in my mind at least, to like translate the measurements to actual constraints. 21 centimeter, we have limits. So 21 centimeter, I haven't discussed at all. The Hera experiment actually has the best limits at redshift 8. So it's halfway through reionization. And we expect, with the data we have in CAN observed, we expect to get enough for a detection. There will be like a 3 sigma detection. And again, human power limited. Data's there. We need people to like analyze, beat down the systematics. But that could be in the 2-year time scale. So it's not 20, but it's not tomorrow.
Is there any even in principle prospect you could learn more about this from the CMB? So we have the town measurement bomb.
Mhm.
Are there, shapes of that E-mode peak or things like that? If you had a measurement that was twice as good or 3 times as good, could you imagine they're maybe relevant or?
I think so. So I'll say, first off, KSC is promising, because Rini can tell you all about it. The second, Lightbird and more futuristic missions are gonna reduce error bar by factor of 4, 3 or 4 or 5. And that's enough that you can start to distinguish things better, but also that you might be able to distinguish the high and low Z contribution to tau. There was this whole kerfuffle some years ago where folks claim that there cannot be more than some tau redshift larger than 15, smaller than something. And then it turned out the errors were bigger because the modeling was a little more constrained. That if you can do that better, you can separate the E-mode contribution better into the high and low redshift. That has insights, because that tells you what's happening, say, here versus here. But that's still 1-point function. I think what you would want indeed is patchy realization. You want something that tells me the clustering of tau. And I don't know how well, say, Lightbird can do it, but I'm sure someone does. I don't know. But there's prospects from the CMB.
Well, antibodies would be micro-3 rather than 5. On the town, not the super large scale. But you'll see. I didn't do like with him.
I can do tau, because then you're in space.
Then guess the fact that I guess KSD can pull out some of the democratic. Because
If it takes too long, yeah.
Yeah.
Yeah, that's right. That's right. Thank you all.
¿Va a ser la última pregunta?
Felipe,
Mucho gusto.
Muy bien, que le quite stop recording, there you go.